Imaginary engine receives heat and does work on a slowly moving piston at such a rate that the cycle of operation of 1 kg of working fluid can be represented as a circle of 10 cm in diameter on PV coordinate system, on which 1 cm is equal to 300 kilopascal and 1 cm is equal to 0.1 meter cube per kg respectively. Here it is a linked and answer question. It consists two questions such that the second question answer depends on first question answer. Here the first question is the work done by the system is. Here the options are 235.7 kilojoule per kg, 2357 kilojoule per kg, 0.2357 kilojoule per kg and 2.357 kilojoule per kg. And here the second question is if the thermal efficiency of the system is 70.2%, the heat rejected by the engine in a cycle is. Here the options are 1000 kilojoule per kg, 100, 0.001 and zero point 0.1. Coming to the solution for the first question, here the work done by the system. In the given data, an imaginary engine receives heat and does work on a slowly moving piston at such a rate that the cycle of operation of 1 kg of working fluid can be represented as a circle of 10 cm diameter on PV coordinates. So consider PV coordinates and draw a circle. So this is the given cycle of 1 cm diameter. But we know that work done by a thermodynamic cycle is equal to the area under the PV diagram of the cycle. So here area under the PV diagram is equal to work done in the cycle is equal to area under PV diagram, which is equal to pi by 4 d square. So 1 is equal to pi by 4 into 1 square. Sorry, it is 10 centimeter diameter. So here it is pi by 4 into 10 square, which is equal to 25 pi centimeter square. And here coordinates are taken as 1 centimeter is equal to 300 kilopascal and 1 centimeter is equal to 0.1 meter cube per kg. So the scales are given like this. So here just substitute those two values, that is 25 pi into 300 kilopascal into 0.1 meter cube per kg, which gives a value of 2357 kilojoule per kg. So here the correct answer is, in the given option, the correct answer is B. B is the right answer. And coming to the second question, if the thermal efficiency of the system is 70.2%, the heat rejected by the engine in a cycle is. Here thermal efficiency of the cycle is equal to the net work done by the cycle by heat supplied to the system. So here heat supplied can be calculated by using this equation, that is work done by the cycle by thermal efficiency, and is equal to, here work done is 2357 kilojoule per kg and the efficiency is 70.2, that is 0.702, which is equal to 3357.5 kilojoule per kg. Now we know that the net work done is equal to the heat supplied minus heat rejected. So here heat rejected is equal to the heat supplied minus net work done by the cycle, and is equal to 3357.5 minus 2357 and is equal to 1000.5 kilojoule per kg. So in the options, the right answer is B. B is the right answer for the second question. A carbon steel member is being machined at a cutting speed of 0.5 meter per second with a tool of rake angle 8 degrees. The width of cut and uncut chip thicknesses are 5 mm and 0.25 mm respectively. The average value of coefficient of friction between the tool and chip is 0.3 and the yield strength of the material is 400 megapascal. Assume Lee and Schaffer's relation. The force required for cutting is. Here it is a linked answer question. It consists two questions such that second question answer depends on first question answer. Here the first question is the force required for cutting is. Here the options are 589 Newton, 421.3 Newton, 91 Newton and 200 Newton. Here the second question is determine the Power consumption during the process. Here the options are 294.5 watts, 200 watts, 165.6 watts and 133.3 watts. Coming to the solution, first write down the given data. So here velocity or cutting speed V is equal to 0.5 meter per second and rectangle alpha is equal to 8 degrees. The width of cut and uncut chip thickness is, let us say, T1 is equal to 0.25 mm and T2 is equal to 0.5 mm. The average value of coefficient of friction between the tool and chip, that is mu, is equal to 0.3, and the yield strength of the material, that is sigma y, is equal to 400 megapascal. And from the mu, it is the coefficient of friction. From this, friction angle can be obtained, that is lambda is equal to tan inverse mu, which is equal to 0.29 radians or 16.6 degrees. According to Lee and Schaffer's relation, the pi plus lambda minus alpha is given by pi by 4. Here the relation between pi and lambda and alpha is equal to pi by 4. From this we can get pi, which is equal to pi by 4 minus lambda plus alpha, and is equal to 36.4 degrees. So here we have all the angles: shear angle, rake angle and frictional angle. Now just calculate here the shear force component, and is given by Fs is equal to tau s into As, that is here shear stress, the maximum permissible shear stress into the cross sectional area of the shear area, and is equal to tau s into, here the shear area is T1 into W by sin pi, where W is the width of the workpiece, and the maximum permissible shear stress is given by half of the yield stress, which is equal to 200 megapascal, because here yield stress is equal to megapascal. So on the substitution of all these values, the shear force component is equal to 200 into 0.25 into 5 by sin 36.4, which is equal to 421.3 Newton. Now calculate the resultant component of the machining forces, which is equal to Fs by cos pi plus lambda minus alpha. So and is equal to 421.3 by cos 45. So which is equal to 596 newtons. Now calculate the cutting force, and is given by Fc is equal to R cos lambda minus alpha, and is equal to 596 cos 16.6 minus 8, which is equal to 589 newtons. So this is the cutting force, and in the option, the correct option is A. A is the right answer. Now consider the second question. So determine the power consumption during the process. Here the power consumed during the process is given by the cutting force into cutting speed. Here Fc into V, that is 589 into 0.5, which is equal to 294.5 watts. So here the right answer is A. A is the right answer for the second question.